going to kick us off today talking a bit about the connection between these martingale frameworks and kind of more recent foundational models.
Thank you. Thank you for the introduction. Is this good? Okay, I have it the wrong way. Okay. Thank you for inviting me here. I'm really delighted to be in London again. And to talk about some, really very new research for me, actually quite unfinished, to be honest. So I'm really be happy to receive feedback. Okay. How do I go next? Oh, with the mouse?
Yeah.
Okay, there we go. Oh, not. Okay. All right, I'll figure it out. Okay, I just have 4 very short sections. And let's get started. So what is prediction for? A bit of a rhetorical question here. So in modern machine learning, prediction is really ubiquitous. We have, computer vision was kind of the first one that fell, that fell to the sway of deep learning. And then we have protein folding, of course, which we all saw in the news very recently for, leading to the Nobel Prize award. And then, of course, we have large language models, which is a great example of generative AI. But actually, it's prediction that powers the generative AI, right? These LLMs are really trained on something as simple as next token prediction in a sequence. Okay, so these predictions are very powerful, but they're often unprincipled, and I don't really mean that in a pejorative way. They work really well, so there's obviously something going on. But they are prone to miscalibration, to fragility, sensitivity to distribution shifts. And of course, classical learning theory offers very few guarantees on predictions made, for instance, using deep neural networks. Again, that's not really the fault of the deep neural network. It's probably just the theory has not caught up yet. Okay, and I'm really trained as a rather classical statistician. We tend to prioritize inference, and like well-calibrated uncertainty quantification is really, what we eat for breakfast. And we really view, I think, prediction as a byproduct of doing good inference. But this rigor that we have in our discipline when it comes to inference is actually its own source of bottleneck, I think. So we have actually very few principled tools for modalities such as image or text. And the predictive kind of machines that are derived from well-principled statistical models, their accuracy really trails black box machine learning. Okay, so I think we can all agree that a two-way exchange that can merge the reach of machine learning and statistical rigor is something that we would all like to see. And I'll just offer 2 illustrative case studies. The first one is really, an example of a machine learning algorithm that is really powerful, that's being deployed a lot in applications now. And I think we really need some type of statistical theory or some kind of theory for safety, for interpretability, for trustworthiness. Okay, and the second case study, it's kind of the other direction of the exchange. So we kind of have a procedure that is grounded in, you could say, classical Bayesian principles, but it just doesn't really scale. And maybe the answer is to evolve towards some type of post-Bayes that can also tap machine learning's predictive power. Okay, so here's the first one that I want to talk about. This is in-context learning. So this is a phenomenon that large language models exhibit. So this refers to the fact that an off-the-shelf LLM, it can adapt to entirely new tasks just by seeing very, very few demonstrations, okay? And this is an LLM that is done training, so you are just interacting with it at training time, at inference time. Okay, so here's an example. You can type this into your favorite, Claude, Gemini, ChatGPT, whatever. And you give it 2 examples that have completions, right? Like a XY pair. The forest is dense. Towering trees with gnarled roots weave a tapestry of shadows. Example 2, the night is cold. The air bites and stars glitter in the frost. And example 3, the ocean is vast. And so you want the LLM to complete this. Okay, so, humans are very good at inferring what the task is without being told what it is, just from, two examples in this case. And the LLM is actually very good at this type of meta learning. So it can first infer the task as something like turn a boring statement into a vivid sentence, right? And then it can complete example 3. I should have given you the completion, but I promise you it does a very good job. Okay, so what is very striking about in-context learning, ICL, is that LLMs are not trained to perform ICL. They're really trained just to predict the next token. And this is why in-context learning is often called an emergent ability. And it's not just something that's kind of cute. It really is, I think, an emerging predictive paradigm that's already powering a growing number of applications. So I'll just tell you, there are many applications, just 2 that I'll highlight. So this isn't a paper that was brought to my attention by some numerical analysis colleagues. You can now build an in-context operator learning machine. So you basically kind of meta train on a bunch of differential equations. And then at inference time, you just have to give it some demonstrations and it can figure out what the operator is, what the differential equation operator is, and then complete the task. So this could really be a new way to solve differential equations using foundation models that are trained in this very specific way. And just as an example, I mean, this foundation model is very small. It's only trained on 19 different types of differential equations. And then what's really happening is every time you're just passing in these conditions, and then the quantity of interest, this QOI, is the solution. So the transformer never sees this differential equation, right? So it's really quite remarkable that it can kind of reverse engineer the operator underlying the condition and solution. Okay, here's another example. It's a bit scary. I think this paper is out in Nature or Science. So it's called Foundation Models for Generalist Medical AI. You could just think of it as something that could potentially replace your GP, your general practitioner doctor. So they basically train this foundation model, and then they use in-context learning to teach this GMAI agent about a new concept with very few examples. So you could use it for something like, here are the medical histories of 10 previous patients with this infection called Langia something virus. How likely is it that our current patient, and you give the current patient's covariates, how likely is this patient to be infected with the same virus? So this really could be, a new way for people to do medicine. Okay, so because in-context learning just works really well, it's very tempting to search for an underlying principle or to claim that there really must be some principled explanation for why it works. So there are a bunch of papers out there that retrofit Bayesian interpretations and explanations onto in-context learning. And I list just a few. And because I think I'm still very behind on the literature, stopped reading at like 2023 or 2024. Okay, so but for every paper that claims ICL is Bayesian, there really is like another paper that will show it's not. And a notable one, I think, comes from Chris Holmes' group here. This is the Falk et al. Came out in 2024. And they show that it's not Bayesian in terms of it violates the martingale condition, which I will talk about. Okay, so at least to me, it's quite obvious that in-context learning in today's large language models, it's definitely not exactly Bayesian. It's probably not even asymptotically Bayesian, and I'll explain what that means. But that doesn't mean it's not perhaps Bayesian adjacent or post-Bayes. There's some type of logic there that I think it would be very interesting to elucidate. Okay, so my second case study is kind of the other direction, where we take something that's very principled statistically, And let's see if we can kind of evolve it towards, from classical Bayes to post-Bayes. Okay, so Bayesian deep learning is something that I've worked on a little bit. And I've always, I don't know, the people who work on this, I think really believe in it. And it's often touted as like this panacea to unprincipled deep learning. So the idea is very simple. You're just doing Bayesian inference and you place a prior on the neural network weights, and then you use the posterior predictive, right? So you average over the posterior in theta. Okay, so this is a good object to work with, but of course it's very intractable for actual Bayesian neural networks because this posterior is very, very difficult to approximate. But I think that's not even my main concern with it. It really is how to select an appropriate prior. I mean, I'm not a Bayesian by training, so I always found selecting priors to be rather mysterious. But certainly for neural network weights, I don't think anyone really has any idea how to put a proper prior, because these weights really don't have any physical meaning, right? Okay. So here's a very simple example where I think you can see that Bayesian deep learning should be doing something reasonable, but it's not. So here's this is a toy cubic function, a cubic function that generates y is equal to x cubed plus noise. But the x's only come from these two intervals, so there are gaps in the support. And we can try to fit a one hidden layer MLP. So here the width is 50, and I'm using a CLU activation function. And what I'm showing you is just a reproduction of, just figure one taken from my colleague Liam's paper, where they look at variational inference, SWAG, and LA stands for Laplace approximation. So these are the three, if you want, simplest ways to do Bayesian deep learning, right? So in variational inference and Laplace, you do need to put a prior. The SWAG is, it's a bit harder to explain, but you're basically averaging the iterates of SGD, and then that's what you use to kind of form your ensemble. But you can see that there are issues with the uncertainty quantification, right? For variational inference, in the middle section from like -2 to 2, the uncertainty is not being reflected, right? It should kind of balloon out a little bit. For SWAG and Laplace, I mean, it does cover the true function, which is in black. But again, it kind of overestimates the confidence a little bit, right? Okay, so I'll come back to that example, but it does seem worth exploring more generalized constructions of the posterior distribution that then gives you this posterior predictive. Okay, and maybe this is something that we could call post-Bayesian deep learning. So it's not like variational inference or Laplace, which is really trying to approximate classical Bayes deep learning, if you want. Sorry, let me just check one time. Okay, so I've worked on both of these problems in context learning and Bayesian deep learning. For in context learning, I have a paper with some colleagues that builds on earlier work I did, where we employ a complexity measure from something called singular learning theory that can detect when the transformer exhibits significant developments over the course of training. And one thing that we can pick up on using this singular learning theory complexity measure is in context learning. Okay, so in terms of Bayesian deep learning, I really only have one work on it, to be honest. Oh no, maybe it's two now, but okay. The main one uses singular learning theory to guide the design of a variational family with guarantees on how big the variational approximation gap is. So originally I was really thinking about talking about this paper, but you've been spared singular learning theory, which is really quite difficult to digest. Okay, so there are some common ingredients to both of these works that I've done before. So there's singular learning theory, there's deep learning. But I always viewed them as very, very different aspects of my research. I work with them on completely with very different groups of people. Oh, I should say that, one of the reasons I didn't go deeper into Bayesian deep learning after I did this paper on variational approximations to Bayesian deep learning is that I was very disappointed to discover kind of theoretically that even if you do really well approximating your posterior using variational approximation inference, that doesn't propagate down to the predictive object. Okay, so if you have two variational approximations, the one that has, a higher elbow could actually give you a worse downstream prediction when you check it into the posterior predictive. So I think that is actually quite a worrying result for Bayesian deep learning. Okay, so in recent months, maybe just in the first half of this year, it actually really spurred by Jeremiah's visit to Monash University to visit David Fraser primarily. I revisited this idea of the martingale-posterior distribution. And this is work from Edwin Fong and Chris Holmes and Stephen Walker. And I first found out about this idea in early 2024, and I just kind of forgot about it. But I've been looking into this area again, and this has also led me to the body of work on Bayesian predictive perspective by Fortini and Sonia Petroni. I don't know if Sonia's here right now. Not. Okay, so I think seeing through this Bayesian predictive lens, problems that seem as different as in context learning and Bayesian deep learning kind of share a common thread. And so I'll, kind of start to pull on that common thread and show you what I mean. Okay, so I think Sonia will do a much better job of explaining this Bayesian predictive approach tomorrow morning. But here's my interpretation. In Bayesian statistics, prediction is not as visible as in machine learning, but it's actually no less central. And so we can view Bayesian inference as accounting for what we have not observed. So this is kind of the future data that is really the source of uncertainty. And this perspective permits you to begin to do Bayesian inference or quasi-Bayesian inference, whatever you want to call it, to begin with the predictive distribution. Okay, so that allows you to then bypass the need to explicitly specify the likelihood and prior. Okay, so here's a slide that just kind of explains some basic terminology. So we'll have P be the probability law of this Y1 to N. And the Bayesian predictive approach really begins by specifying a sequence of one step ahead predictions, predictive densities or predictive distributions. So this capital P naught is just kind of the base, Y1 is in something, and then Pn is Yn plus 1 given all the previous data. And these capital P's may have corresponding densities, little pn. Okay, so there is a sense in which we can say that a Bayesian model underlies or is behind the sequence of predictive updates. So if Y1 to N is exchangeable or P is invariant to permutations, then you really can say that there is a Bayesian model behind this predictive sequence. And this is really by appealing to Di. Okay, or you could relax exchangeability to something called conditionally identically distributed, CID. And this is from Berti et al. And this is another way of saying that the Pn satisfy a martingale condition. And in which case you could still say there is a Bayesian model underlying the sequence of predictive updates, but it's in an asymptotic sense for very large N. So this approach has been used to shed light on algorithms that take the form of predictive updates. Okay. By shed light, I mean to reveal the Bayesian model underneath. And I'll give you an example of that, previous work. And then I think it also really offers a way to be post-Bayes. Okay, so I'll just now circle back to the question of whether in context learning in large language models are Bayesian or not under this lens. Okay, so given a pre-trained foundation model, which I'll denote P capital N, we can really regard in-context learning as an algorithm that returns a sequence of one step ahead updates, right? So you give it demonstrations, x1, y1, x2, y2, up to xn, yn, little n, and little n can be 3, 5, so you don't need a lot. And then it will give you the next token, right, prediction. So we can ask if this algorithm, if these updates behave in a Bayesian way, maybe they don't. Okay, so here's a concrete example of using this Bayesian predictive perspective to assess how Bayesian an algorithm really is. So in this paper by Fertini and Pretrained in 2020, they studied Newton's algorithm. Sorry, I didn't write that down, but Newton's algorithm is a recursive algorithm where you can estimate some unknown mixing distribution G. So the sequence is capital GN. And then that in turn yields a sequence of predictive updates, yn plus 1 given the previous past. You basically just have this GN as the mixing distribution. Okay, so then these predictive updates characterize the probability law of yn using just the chain rule. And Fertini and Petroni show that this law is CID. In other words, CID is another way to just, you can think of it as asymptotically exchangeable for large N. And so in fact, when you use something like Newton's algorithm, it doesn't feel like you're appealing to any Bayesian principles, but in fact, you are, but in an asymptotic sense. So I think it would be really worthwhile to uncover the implicit Bayesian assumptions, if any, underlying in-context learning, just as was done for something like Newton's algorithm. But of course, there are some big challenges. Existing results in this area, in this Bayesian predictive approach, they mostly study predictive updates that are closed form, that are recursive, or plugins. And transformer predictions are really none of these, okay? And furthermore, we already have good empirical evidence that off-the-shelf large language models violate the martingale property required of, first of all, Bayesian learners and of quasi-Bayesian learners. Okay, and this is the paper I mentioned before from Chris Holmes' group. Okay, and of course, just state-of-the-art industrial LLMs, they really operate in a regime that is very hard to do theory for, right? So that goes without saying. Okay, so in my view, we need some type of theory that goes beyond these closed form recursive updates. I think that's very doable. We need to go beyond martingale-based learning. So, we need further relaxations, really. And crucially, I think to do this science properly, we really need to find the right fruit fly. Okay, because we will not be able to investigate industrial scale LLMs, but we need a model that is simple enough to analytically, to be tractable analytically, but still rich enough to reproduce the same type of phenomena as an industrial LLM. So that's probably the hardest thing. Okay, so the first part of this talk is really posing more questions than answers. And now I'll shift to using this approach, Bayesian predictive approach, as like an analytic tool, to reveal the implicit assumptions behind algorithms like in context learning. And the second part of the talk is really about using this approach as a constructive tool, okay, for designing post-Bayesian procedures. And really, I'm going to use transformers as the predictive engine. Okay, so I will briefly review what martingale-posterior distributions are, but I'll start by really, I think, just using Fertini and Petroni's language, because I really view the martingale work as an extension. Okay, so for an exchangeable sequence, with this predictive sequence, capital Pn, we have a weak convergence Pn to F tilde, where this F tilde is the so-called directing random measure of the sequence, and it plays the role of the statistical model. Okay, and this is actually the result that that people use to, say that uncertainty is in terms of missing observations, the missing future observations that you haven't observed. Okay, so this weak convergence result also holds when PN is a martingale, or another way of saying that is the data is conditionally identically distributed. So Fertini and Petroni in various works describe a predictive-based simulation scheme that allows us to draw samples from both the both the prior and posterior laws of F tilde using only the predictive density, predictive sequence. Okay, so that procedure, Fong et al., they relabeled this as predictive resampling. And they do another kind of a further step where they're not really studying the F anymore. They're studying functionals of F, right? So theta of F that they focus on comes from this type of, generalized Bayesian interpretation, right? So the parameter you're interested in is the argmin. It's basically a population risk minimizer, if you want, right? So here, capital F is just some distribution. Okay, and in Fong et al., they show that the predictive resampling procedure can recover the classical Bayesian posterior construction whenever the predictive sequence Pn is the posterior predictive distribution associated to some likelihood prior pair. Okay, so I'll just describe what that procedure looks like very concretely. So now I have a sequence of predictive densities, little p, and let's suppose they satisfy this martingale condition. And there are a few more conditions on theta, but anyway, let's not talk about that. We can now simulate future data via a forward recursion. So what that means is you have your original data y1 to n, you never touch it, right? It just stays fixed. You throw it into your predictive density, you draw yn plus 1. And now you augment the original data by that yn plus 1. And now you have y1 to n plus 1, and you can draw yn plus 2. And then you just keep doing this over and over again. You can't do it an infinite number of times, but so here you might stop at some y capital N. And if you let F capital N be the empirical CDF of this augmented sample, we can talk about this F infinity as the limit when you do really the forward recursion to infinity. And then the distribution theta infinity, the distribution of theta infinity is called the martingale-posterior distribution. So obviously there is something random going on, right? F infinity, every time you do a forward recursion, it's random, right? So that's why it leads to this distribution. Okay, so in practice, of course, if we want to implement this, we have to truncate the recursion at some finite depth, right? So capital N, and then we need to generate multiple independent paths to obtain samples. So every time you do this F capital N and you chuck it into theta, you get one sample from the martingale-posterior. Okay, I hope that was clear. Any questions? Yeah, feel free to stop me at any point. Okay, so for martingale-posterior literature, I mean, it's a very new topic in a way, but it's very active. People have focused on predictive constructions, and by that I mean how to specify the sequence of predicted densities. Okay, so there's the bivariate-copula update. It's a recursive update in the original martingale-posterior paper. There's something that is meant to target non-parametric density estimation. That again uses a recursive copula update. There's some work that studies kind of plug in parametric predictive densities. So PN just uses PY given theta n hat. Okay, so it's a very different type of object, but in this paper by Edwin Fong, he studies the asymptotic properties, and they're good. Okay, there's quantile-MGP. Again, it's trying to do some quantile estimation, but again, the predictive update is recursive copula. And finally, there's this paper it uses predictive distributions that are implicitly defined with neural networks. But the neural network is not a transformer. It's just kind of a generative neural network that gives you an implicit distribution. Okay, so I'm sure there are more papers. Like I said, I'm behind on reading papers. I fear I will always be behind on reading papers. There's just way too many nowadays. We should all write less papers, right? Okay, so I don't know, at least to the best of my knowledge, that transformers have been used as predictive engines within the MGP framework. And of course, we shouldn't just use transformers because they haven't been used yet for something. But I think they really are perfect for this framework. And that's thanks to their in-context learning abilities that I talked about at the beginning. So there's no need for constructing the copula, that you don't need to tune anything. There's no bandwidth to wrangle with. You really just pass the data in and you can get your sequence of predictive updates. Okay, but the choice of the transformer matters. Not all transformers are equal. And, you know, like I said, it might be tempting to just chuck in an off-the-shelf LLM that you download from Hugging Face for the purpose of trying this out. But, you know, I think the Bayesian-ness of these off-the-shelf LLMs are really kind of debatable. And we do need some type of, I think some type of Bayesian aspect to the transformer. Okay, so in the following section, I'll motivate why I think prior data fitted networks, PFNs, are really well suited to being dropped in as a predictive engine for the MGP, for the martingale-posterior. Okay, so this is a pretty new area, prior fitted networks. And the idea is really simple. The paper doesn't really present it like this, but this is how I interpret it. There's a really classic result that the Bayesian posterior predicted is optimal on average with respect to the KL divergence. So specifically what this means is, suppose your data arise from some mixture model. And so you have a Q, which is a predictive density that takes in data Y1 to N, which is it's arbitrary for now. And we can look at the KL divergence between this PY given nu and Q given the data. Okay, so this quantity is random in two sources, right? There's the nu that's random, the parameter, and then also your data is random. So that's why I've written it like this. And now if we average over the source of randomness in the parameter and in the data, we can show that the unique minimizer over Q is the Bayesian posterior predictive density corresponding to that original likelihood prior pair. Okay. So PFNs, it's a type of transformer, and it basically uses this optimality result as a meta-learning objective. That's how it trains. Okay, so specifically for a PFN, you train on a meta data set of data sets. Okay, so you have a data set and each point is a data set. And the data set is basically drawn using this mixture model, right? So to draw from this mixture model, you have to first draw from the prior and then you draw IID given that parameter. So you draw many things from the prior and each one generates a data set. And then that KL divergence has an entropy term that doesn't affect the optimization. You drop it and you parameterize that predictor Q by a transformer with weights W. And then the training objective just is as simple as using negative log of the transformer predictive output. Right. So this network was called a prior data fitted network in the original paper that introduced this. And then, you know, that group has since started a startup, and then they've really ramped up their training, their capabilities. So you might call this one like kind of baby PFN version 1.0. I don't know what version they're on now, but in follow-up work, the same team built a foundational PFN. So now there are millions of synthetic data sets, and it's not just generated from one likelihood prior pair. It's this vast mixture of likelihood prior pairs. And it covers a really wide range of tabular classification and regression tasks. So tabular, I'd never heard of this word tabular until I got into ML, but it just really means like the classic type of data that we tend to work with, not images, not text, like not structured, right? Okay, so training a transformer on this very vast meta distribution yields what they call TabPFN. And it's designed for really low sample size tabular tasks. And it is now the state of the art for small data tabular classification and regression, and it delivers the prediction in just a few seconds. So you really have nothing to tune. You just do a forward pass of your data through the transformer. And it outperforms the previous state of the art, like gradient boosted decision trees. So, for many years when I worked on machine learning, on deep learning, I would encounter statisticians telling me that, well, it doesn't work for, small sample size. But, here's an example where, okay, it really does work for a small sample size for tabular data. So we don't have that excuse anymore. Okay, so of course, viewed as an algorithm for just producing predictive updates, and I kind of mentioned this before, the TabPFN, it's not recursive. Okay, so there's really no relationship between the n+1 update and the nth update, right? And that's actually also true for the classical posterior predictive. Okay, so there's actually something quite kind of unnatural about assuming these updates are recursive, I think. Okay, and it's not plug-in. You cannot write it as yn given xn of some theta hat n-1 based on the previous data. The transformer weights are fixed and they really do not play the role of classical parameters. And TabPFN is only kind of semi-permutation invariant. There's some things that are done to the architecture to kind of encourage permutation invariance, but it's not strict. And then at training time, they do ensembling to encourage more permutation invariance. But anyway, all to say that it is not exactly exchangeable, right? Okay, so I'll finally show you some results that I have, but they're quite preliminary. So, okay, so TabMGP. I'll need a better name to get it published in NERDS. But okay, TabMGP is the martingale-posterior with TabPFN dropped in as the predictive engine. It's just my temporary placeholder of a name. And the predictive update really is, it really is simple. I'm not gonna tell you otherwise. So this is what it looks like. You have your X current, Y current, and you just call .fit. Okay, so you now have this object. And then you have your next X, your query. Let's call it xn+1. Oh, sorry, let's call it X next. And then you just take that same object, you say predict the probability of X next, right? And then for Y next, the corresponding Y, you just draw from that probability vector. Okay. And then there's of course a parallel function for doing this for regression. But of course you might wonder, transformers are really designed for categorical, for classification tasks, right? It's not designed for regression. So you could add a regression head if you want to, but what they do in TabPFN is they basically discretize the response space, right? This is not great. But if you're doing, low dimensional regression, like when the Y is low dimensional, this is okay. Yeah, but this is probably something that they need to improve on. Okay, so of course, this is just the predictive update for the Ys. For predictive resampling of xn+1 to capital N, sorry, that should be a subscript. I actually don't really know what I should do. TabPFN is not good for this because the x's could be very high dimensional. And I don't see a lot of guidance in the martingale-posterior literature besides using Bayesian bootstrap. And so that's what I've been doing. Sorry, when do I have it until again?
15.
15. Okay, so you can see that there really are just two hyperparameters involved in TabMGP. I need to decide the recursion depth and then the number of this forward recursion path. Okay. So I'll just circle back to that toy cubic regression example I had and just drop in TabMGP and see what we can do. And here's the result. I mean, so what is happening here is I truncated the recursion at 500. And this is based on just the original data set is 20 points. Okay. And I did not take many TabMGP samples because I wanted to make it kind of comparable to deep ensembles where they often just use, 5 or 10 in their ensemble. So here, this is the ensemble you get from just drawing 10 TabMGP posterior samples. And I mean, yeah, I don't know. I don't know how to judge these results really, but it does look a little bit better than, I should have juxtaposed these, sorry. I think it does look a little bit better than some of these baseline methods, right? It almost covers, it's not, it's picking up kind of this gap in the middle, and then the uncertainty is kind of fanning out at the tails as it should. Let me jump back. Okay.
It's a different scale. The other plot is minus 200, 200, and this one to minus 100. For my repeat how
Oh,
visual comparison.
oh yeah, cool. Oh, that's a good point. Let's see. Oh, I see. They did do -5 to 5. I think I did maybe -4 to 4.
Oh, I look at the y-axis.
Yeah, that's interesting. I'll have to check. Thanks for pointing that out. That's strange. I wonder, okay, there might be something kind of that's not matching with my with their setup. I'll have to check. Okay, I mean, so could we use TabMGP as a new way to do kind of post-Bayesian deep learning? Probably not yet. And the issue is a lot of Bayesian deep learning, the research is really concentrated on structured data, such as images. And TabMGP currently cannot be applied in that regime because the backbone that it's based on, this TabPFN, is really restricted to tabular type of inputs, right? But I think it's not ridiculous to think that this PFN framework could be extended to richer modalities in X, such as image or text. But let's see if that happens. Okay, so now just in the final few slides, I will show you some maybe a more concrete application that I've fleshed out a little bit more. And it really sits outside the usual deep learning type of benchmarks. And I think it's maybe of more interest to statisticians. So here I'm going to focus on a functional theta that indexes a standard probability model, but not necessarily the true one. So that's not an assumption we need to make. And I'll compare other posterior constructions with the TabMGP on both synthetic and real tabular data sets. And the comparison is in terms of coverage. Okay. And this footnote, yeah, so this is just saying that I was kind of surprised in Foam et al.'s original paper on martingale-posterior distributions that when theta is, in this case, indexing a standard probability model, that they do not recommend using their method. They recommend instead using the Bayesian bootstrap. So I don't really understand why. So maybe just the recursive copula update is too slow to justify its use in this case. But anyway, this is the setting I'll examine. Okay, so the baselines are, well, Bayesian bootstrap, which is, you can view it as a special case of the martingale-posterior construction. And then I'll just also have like a classical Bayesian posterior with an uninformative prior on theta. Okay, so the synthetic experiments I have, they just adapt some previous experiments in Wu and Martin that study what they call like the learning rates. And the learning rate is basically the temperature in your Bayesian posterior. Okay, and then I'll have some real data sets that I examine at the very end. Okay, so coverage, I really mean it in like a frequentist sense. So you have y1 to n drawn from some f naught, and you just want to check if theta of f naught is in that credible region constructed using the data, and then the source of randomness is in the data itself. Okay, and for real data sets, we will not know the true f naught, so we will not know the true theta f naught either. And I'll just use the MLE on the entire data set as the ground truth. And I'm not sure that's the best thing to do, but. Okay, so here we have a data generating process. We just have really logistic regression. And then in the model that you use, you misspecify this link function. So this is a Gaussian mixture, but you still use the cross entropy loss, of course. And there's a parameter here called A, and the smaller it is, the stronger the misspecification. So in this table, it's 3 values of A, and as we go down, it's more heavier misspecification. And so BB stands for Bayesian bootstrap, and then the number in the parentheses is the depth of the forward recursion. So this is kind of arbitrary right now. I set it at 250 and set it at 500. You might wonder why the Bayesian bootstrap seems to be doing really poorly in terms of coverage. And that's because we really just have we specifically focused on low data settings. So n is equal to 20. This is not a great setting for Bayesian bootstrap. Okay. What else do I want to tell you? The standard classical Bayes posterior, it covers pretty well until the misspecification starts to really kick in around the bottom of the table. And TabMGP generally performs pretty well in terms of coverage. This last column, you can consider it the size of the credible region. Oh, I forgot to say the dimension of theta is 10, so not very high dimensional. And so we can see that like the size of the credible region really depends a little bit on, your recursion depth. The further you go, the bigger it is, which kind of makes sense. So some like kind of cute visualizations you can do is just looking at these posterior distributions. There's a TabMGP, the Bayesian bootstrap. Sorry, by Gibbs, I just mean Bayes. And then, we have the population plotted, the MLE plotted. And so this is for each of the 10-dimensional theta vector. Yeah.
That's why the width depends on the depth of the recursion.
Oh yeah, that I think can be answered in the next jellyfish plot. So so this is looking at the TabMGP. Okay, so as we do forward recursion, we have more and more data, right? And at that point in time, we can go and solve for the theta. And so this is the evolution of theta along these forward recursion paths. So each path is kind of one forward recursion, and then we're plotting all the thetas. And so you can see as you go further into the recursion, it can start fanning out a bit more, right? Whereas in the beginning, it's kind of staying close to where it started. Yeah, but of course, it's not always like this, but this is what tends to happen. So, yeah.
So if you were to push the recursion that's really long,
Yeah.
under the martingale assumption, you would expect some convergence.
Yes. Yeah.
Do you see any evidence that that's not happening?
There are definitely some cases. I should have put one that shows you what it looks like. But yeah, I think that can definitely happen. So I think a diagnostic like this is really important to use so that you don't just blindly trust the samples coming out of the TabMGP. I mean, maybe, I don't know if any of these examples. This one is fairly well behaved, I suppose. Here's another example of just doing linear regression. And the misspecified model is that you have these dependent errors. And again, there are these parameters you can play with. And as you go down in that table, the misspecification is getting stronger. And here again, we see that the classical Bayes coverage is very good until maybe you get down to the third row where the misspecification is heavier, that it undercovers. But in general, the TabMGP is good, and the Bayesian bootstrap is again not really doing well because of the low sample size. A bit faster. And another linear regression example where the misspecification is in the error, you've assumed that it's a t distribution. So as the degrees of freedom decreases, it's stronger misspecification. But here, actually, the classical Bayes is working pretty well in terms of coverage, but it is kind of creating confidence regions that are maybe a bit too wide, okay, compared to TabPFN. Okay, so these are all pretty toy examples. We just haven't finished the real data. We have much kind of fewer results to show here. But okay, so here are just 3 OpenML classification data sets. And we're targeting, again, 95% coverage. We're taking n is equal to 50, and then the n total I've displayed here. And the dimension of theta varies from 4 or 5 to 66. Okay, so actually, classical Bayesian, the posterior really works pretty well, except maybe for this data set, it's a bit too conservative. And the TabPFN is not really working super well, I would say. And I don't know really why. I think we just have to dig deeper into these diagnostics, and I just have to do the forward recursion for a longer amount of time. Right, not just like maybe 500 was enough for synthetic data, but not in real data. Okay, and then here's my last one on just regraphing data sets. Again, we're seeing like not super great coverage for some of these data sets. And again, I think it's just because we haven't done enough forward recursion, enough samples. And I just have to kick up the computation. Okay, I think I'm already out of time. Okay, here's my takeaway slide, my last slide. So I think the post-Bayes agenda might be advanced using the predictive power of foundation models. And I think in the other direction, maybe foundation models can be made more transparent if we learn to interpret them through some type of post-Bayesian lens. Okay. Thank you. Thank you for your attention.
Thank you so much. Yeah, probably we have some time for questions, so Cedric.
I was just gonna say, I think this is a very nice idea of simulating recursively from a model like TabPFN.
Yeah.
But some of that relies on the model being accurate for really long context sets, and that depends very much on how the TabPFN is trained.
Yes.
Right?
Yes.
What is the length of the typical sequence that it's trained on? When you use this frequential loss, how does the accuracy behave as the context size increases?
Yeah, absolutely. So in the original PFN, they really did not train on very long context, right? But if we take a page out of how LLMs have developed, like the maximum context window has just kept growing and growing. And I think that will probably also happen for something like TabPFN. But yeah, if it only ever sees during pre-training, very short context, then we should not be using it to do the forward recursion kind of past that window, I would say.
So much for talk. I was just wondering if this stuff extends nicely to, say, dynamic or longitudinal data at all, or have you only considered static something?
Oh, I don't really know, actually. I think this. Maybe there's already some work on using MGP for kind of time series data, but I'm not sure. I think in the original papers, it's really kind of the IID setting.
Maybe you can start doing like a TabPFN for time series, because I imagine you need to train different models. I
Yeah.
thought what was really interesting is when you showed the results of regression models, because you remarked earlier that they discretize, and so actually the standard-based posterior is fairly competitive in that setting,
Yeah.
which is encouraging.
Yeah.
Because it tells you that you do need the right kind of generative tool to do this. And
Yeah.
actually, it's the wrong generative tool for the regression task by virtue of its design.
Yeah.
And conversely, you could actually come up with something that works in that setting as well. So I thought that was like a really nice little nugget.
Yeah,
Sorry, it's more a remark, not a question. But
Yeah, no,
I thought
I
it was
agree.
an excellent presentation, putting all these things together.
No,
that
thank you.
have been like percolating. I thought was very interesting.
Thank you, thank you. Yeah, I agree that for the regression, I don't know how much I trust TabPFN for regression. It's state of the art, but this is just in terms of like MSE. It's a different metric.
Hi, maybe I want to ask about your general opinion about the very first part, right? So you
Yeah.
already mentioned that with the big language model, right, this in-context learning is not that Bayesian.
Yeah,
Okay, so how should people in that role, right, claiming that the in-context learning is Bayesian, go forward,
go what?
go forward in terms of research?
The people that have published the papers that ICL is Bayesian?
Yeah.
I mean, I think, okay, they've redefined what it means to be Bayesian in those papers. So in that sense, maybe, okay, they're correct, but I think those papers, when they say it's Bayesian, it's like a placeholder for saying there's some principle governing this. And I don't know if they're that attached to being strictly Bayesian. So maybe we just have to hold people a bit more accountable how they write their machine learning papers. I don't know.
Probably have time for another couple of quick questions, but maybe in the meantime, on next week, we can often. And I actually did have one.
Yeah.
Kind of a second question. When we see those jellyfish plots.
Yeah.
Do we have any empirical diagnostic or is there any work?
Yeah, that's a great question. I was gonna have a slide on that, but it basically, in the original foam paper, they don't track the thetas because it's expensive. They just track like, you know, the original like PN, the original density at the data set, Y1 to N, like minus P capital N, which is like the recursion as it grows, right? And they're tracking some type of like functional norm there.
Is that because it's fundamentally uninteresting?
No, I think they do track that as like as a proxy to tracking data.
Okay.
Yeah, but it's also hard to say like when it's really small enough that it's converged. So yeah, I think that's a good area to look at actually.
Well, let's thank Susan. once
Thank
more.
you.